Tonight's speaker is Dr. John Taylor, who obtained his first degree, a Masters in Astronomy and Astrophysics from the University of St Andrews, before studying for his PhD here at Keele, supervised by Pierre Maxted, entitled Eclipsing Binary Stars. Well, we don't seem to have travelled too far from tonight's talk. Postdoctoral positions followed at Niels Bohr Institute in Copenhagen, before moving to the University of Warwick, back to Keele, where he has been a permanent lecturer since 2011. Dr. Taylor also does a great deal of support for the wider scientific community. He and I have been out on various sites, outreach bits and pieces over the years, including things like refereeing academic papers, grant applications, sitting on telescope, time allocations, etc. So with no further ado, I'm going to hand over to tonight's main speaker, Dr. John Taylor, talking about binary stars to the rescue. Thank you very much.
You clearly have been reading my staff profiles. Okay, I'd like to begin by thanking the organisers for inviting me to give this talk, and also to George for having a great introduction, and a quick reminder that it is a calm before the storm, so careful on your way home tonight. Okay, so I was asked to talk on the subject of my research, which is binary stars, and I blithely thought, let's do binary stars to the rescue. I'm not sure if I really figured out at the time what I'm trying to rescue. If you're stuck in the middle of the Atlantic Ocean on a life raft, this is not helpful. But if you are a theorist trying to understand how stars work, what I do is very important. One more little thing I want to make here, it is take away my name. Oh, there we are. There we are, flawless. And put in my research name, because John Taylor is just too boring. Okay, so let's have a little bit of audience interaction. Who can tell me what this picture is in the back?
Van Gogh.
Sorry?
Van Gogh.
It is indeed, yes. Remember the name?
No.
Starry Night.
Over the Rhone. Yes. Next question. Where's the binary star? Thank you. Okay, let's take it piece by piece. Can you recognise the constellation?
Big Dipper.
Yes. Or the Great Bear, or the Plough, or to give it its proper name, Ursa Major. Now, I've got a fancy tool that's just been handed to me, which apparently points at the screen, but comes out on the computer as well. Let's try that. I'm not having fun with technology today. Right, okay, so it's back to the mouse then. Okay, so this is Ursa Major. As you can see here, one of those objects is a binary star. Anybody want to take a guess? Yes?
It's the second one up at the top.
You mean that one?
Yeah.
Okay, we have somebody who knows what they're talking about. What is it?
To be fair, John, you did teach me very well.
Thank you. The one you'll be in the post. Do you remember the name, though?
Mizar?
You do indeed, yes, well done. That is the binary star.
Mizar and Alcor?
Yes, so if you look closely, Mizar and Alcor are two stars very close together. You can't see these in the picture because this is not an actual picture of the sky. And they are separated by 12 arc minutes. 1 arc minute is a 60th of a degree, so to give you an idea, 12 arc minutes is a bit less than half the size of the full moon on the sky. But if you look at the brighter of those two, and if you look closely, that's two stars as well. We call them Mizar A and Mizar B because we are not inventive. And if you look even more closely at that, you'll find that both those stars are actually binary stars. So therefore, Mizar itself contains at least 4 stars. So let's continue with this. Who can tell me where the binary star is here? Yes?
The big thing in the middle?
Yes. It is that thing there. So what is happening here is we have a binary star in the middle, we have a big massive star, and we have a small massive star. And they're orbiting each other every 8 years. And they're in quite an eccentric orbit, which means instead of being in a nice circle like this, they do like that. And that means also that when these two stars get close to each other, each time in the orbit, we call that periastron, the massive small star ploughs through the atmosphere of the massive big star and chucks a pile off into space. And we get one of those concentric rings. The orbit is every 7.9 years. That means we get a concentric ring leaving every 7.9 years. And this is an image taken by the James Webb Space Telescope, which shows up to 17 rings if you look off to the right here. And the extreme regularity of these rings occurs only because we've got a binary star system. For the experts in the room, the central object is a Wolf-Rayet star. It's actually WR140. Okay, next, which way's forwards, which way's backwards? Okay, who can tell me now? Go ahead.
The big one there and the big one there.
That one and that one binary?
Yeah.
No.
What?
Yes?
Are they two separate sets of binary stars?
This one is Beta Centauri, and that's common or garden boring.
Is it the red circle?
No. This one over here. So this is the constellation Centaurus. It's one of the biggest, best known ones in the southern hemisphere. We see along the galactic plane when we look through Centaurus, so there's lots of stars. It's a very, very nice place to be. This one here, though, is Alpha Centauri. That's my favourite. I'm going to tell you what's special about that one.
It's close.
How close?
Very.
It is the closest star, or binary star, to the Sun. Alpha Centauri itself contains two stars, A and B, and they're separated by about 14 arc seconds now. And in terms of angle, if you go out tonight and look out at a star, the Earth's atmosphere will blur the picture you see by around about 2 arc seconds. If you go to an observatory on top of a mountain somewhere, that blurring is around about half an arc second, and that's why astronomers stick telescopes on top of hills. And so at 14 arc seconds, this is easy to see. And in fact, Alpha Centauri A and B have the distinction that they are the only binary star where you can see the two stars, and it's possible to see an entire orbit within one lifetime, because the period is 80 years. Unfortunately not from this latitude, but there you go. Someone did mention the red circle at the bottom. That is Proxima Centauri. It's the third star in the system. It appears to be a long way away because this thing's so close. But Proxima Centauri is also interesting. It's very small, very low mass, and it has a planet with a period of 11 days. And because the star is so small and cool, that planet is in the habitable zone. In other words, it's at the right temperature to have liquid water on the surface. I would think it's probably rocky, so it may well be the closest habitable planet outside our solar system. It's definitely the closest planet, probably the closest habitable. Oh, therefore definitely also the closest habitable planet. Okay, let's go to another one then. This might be easier. I'm going to tell you what this one is. I thought no one would know. How about now? Yes.
Is it serious?
It is serious. Well done. The image on the right is from the Harry Potter fan zone. The image on the left is in the Hubble Space Telescope. I know which one cost more. Can we tell me what's important about Sirius, from our point of view? It's the brightest star in the sky, apart from our sun. And it's also visible right now. It's a winter object in the northern hemisphere. So if you go out tonight, look south, find Orion's belt, and go down and left, you've come across a bright star. It's that big thing in the middle. Has anyone seen the binary bit yet?
Star just below it.
Little thing there, very, very small thing. So Sirius has a little piece of history here. Back in 1844, the German astronomer Wilhelm Friedrich Bessel pointed out that its position appeared to be wobbling in such a way it was being orbited by something. He couldn't see what was orbiting it because it was too faint, but if we move forward to 1862, the great American telescope maker Alvin Clark was testing out a new telescope, pointed it at Sirius, noticed that little thing down there, that is Sirius B. That is what is causing Sirius A to wobble. And Sirius B, despite the fact that was originally the more massive star in the system. But massive stars evolve more quickly, so it's been born along with Sirius A, it's gone bang in a supernova explosion, and what we see is a remnant of that, which is just the core. It's what we call a white dwarf. To give you an idea of the scale of that kind of thing, they're around about half the mass of the Sun, but they're around about the size of Earth. They're way smaller, so they're extremely dense objects. Right, one more. Anybody want to take a guess? Okay, I've thrown you a slightly trick question here. The answer is probably half of the stars are binary. I can't tell you which. I probably could if I spent a week sat at my computer. I have better things to do. The point I want to make here is that binary stars are all over the place, and we do therefore need to worry about them, because if we don't, our results will be wrong. So I'm now going to go to a slightly more serious slide and try and collect the reasons why I do what I do. So, the first point is that binary stars are all over, and that's because they are a natural outcome of the star formation process. To illustrate that, I've put a little movie here from a theoretical simulation done by Matthew Bate, now Professor of Astrophysics at the University of Exeter, where he shows how a binary star may form. What we know is that binary stars form a lot of the time, especially in massive stars. Massive stars are mostly formed in binaries or triples, massive stars less so, and therefore, if we try and observe stars and figure out what they're doing, if we don't account for the fact that half of them are binary, our results aren't reliable. So even if you hate binary stars, as an astronomer, you do have to worry about them. The next point is that they're actually very, very useful for understanding stars. So if I look out at the night sky, I could do that tonight actually, it's nice and clear, and just take a point of light. Now, based on the colour of that light, I can get a fair idea of the temperature of the star. I could guess its radius, I could guess its mass. It's nothing more than a guess. That's not very useful, not very reliable. Whereas with binary stars, we can measure both of those things, and we can do it to 1% or better. So that's why I like it. It's because it is the best way of measuring the properties of normal stars. And there's a third one here. They make all sorts of strange stuff. Characteristic variables are little objects, very, very old binary stars, where a white dwarf is gradually eating its companion. They sit there really, really faint for decades, occasionally get 1,000 times brighter back down again, sometimes 1,000,000 times brighter and back down again. And the cousin of those is X-ray binaries, where instead of a white dwarf in the middle, you have a neutron star, and the eating of the companion star, it causes such extreme emission of radiation, a lot of it comes out in X-rays. Nobel Prize in Physics in, I think, 1980 for that one. If I go to supernovae, then there's a certain type of supernova called the type 1a, which comes from binary stars. And the great thing about those is whenever they explode, they're pretty much always about the same brightness. So we can use those to work out the size of the universe. Nobel Prize in Physics, 2002. Gamma ray bursts. Now they are weird things. Back in the 1970s, the Americans sent up satellites into low Earth orbit to try and pick up very, very high energy radiation. The idea being that they thought the Russians were building atomic weapons and they wanted to find out if there were any tests. What actually happened is that they discovered a great pile of these very, very short flashes, like 2 seconds, 30 seconds, all over the sky. Technical term, isotopically distributed, definitely not coming from Earth. It turns out that half of those are caused by binary stars. Two stars merging together cause this extreme and very, very short flash of intense, very high energy emission. Finally, gravitational waves. That's a recent entrant to the work in astrophysics. Now we have two black holes, or two neutron stars, spiraling in together. When they do that, they emit energy as gravitational waves. They distort space-time. These days, if you have millions of pounds and 25 square kilometres in Louisiana, you can build an array which will detect that. It's an extraordinary piece of engineering. It's now done at 3 places in the world. Nobel Prize in Physics, 2017. So I'm going to claim now that binary stars are at the forefront of stellar astrophysics and are therefore worth having a look at. My next point is that I'm not really going to go into the nitty-gritty of this. This is kind of a why and the results talk, but I just want to impress upon you that inside all of this, there's a great pile of maths working. This is the kind of thing I'm talking about. These are all the equations I've just taken straight from my third year undergraduate module to do with binary stars and celestial mechanics. And the message here is that, trust me, I've done this stuff. I pretend to know what I'm doing. The good news is, this is the only slide with equations in. So I'm not going to explain them all. Right, so now I want to give you a little bit of history and try and illustrate that with the different types of binary star we have. And I'm going to order them according to how we observe them. So, can anybody guess when the first observation of a binary star occurred?
16 something.
Earlier. Anybody want to move? About 1200 BC. The ancient Egyptians made a series of calendars discussing lucky and unlucky days, and in the Cairo calendar about 1200 BC, there's clear evidence that the god Horus has events occurring every roughly 2.85 days. And some people in Finland have tracked that down to the eclipses of the eclipsing binary star, one of the brightest stars we know in the sky, called Algol. Naked eye object, you could probably even see that from in the middle of a town, maybe not a city. And that has a very, very deep eclipse every 2.9 days, and it appears to be in the Cairo calendar. So that means that the subject I'm doing is about 3,200 years old. Okay, next question then. Anybody want to guess the first time a calculation was made about what an eclipse would look like? I mean, not observing these things, but actually calculating with an understanding what's going on. It's before the 1600s.
1400s.
Keep going.
Is it like the Babylonians?
No, but not too far off. Okay, so we go to around about 150 AD, and the Roman scientist Claudius Ptolemy produces his great work, the Almagest. And in that, chapter 8, book 6, he predicts what an eclipse would look like, an eclipse of the moon in front of the sun. So a solar eclipse, and the red points here are what he predicted. And the green line is a modern prediction using computer code. I should remember, this is before computers. This is before even probably having books. This is before he knew the value of pi, the ratio of the area of a circle's circumference to its radius, diameter. He was using 3 and 17 divided by 120. But he still managed to get something pretty good. And I also want to mention here, whilst I'm at it, that we might have a slightly Western-centric view here, because Ptolemy's Almagest, it was originally called the Magna Syntaxis, the Great Treatise. But it was lost to the Western world for hundreds of years during the early Middle Ages. But the Arabs took it, they copied it, they were great astronomers in their own right, they built observatories, and in around about 1200 AD, the Almagest came back, but now with the Arabic name. And Almagest stands for the greatest. So we have a lot to owe people who are not in the Western world. So let's continue on a bit. The next person I want to pick out is a German mathematician and astrologer, Johannes Kepler. Bear in mind that back in the 1600s, astrology was a respectable profession. I'll stop, I won't comment on that. And he was employed and then required to produce a reason, to understand the orbit of the planet Mars. Again, Mars is visible tonight. I was looking at it on my way over to the room, to the building tonight. It's just next to Castor and Pollux in Gemini. And the weird thing about Mars is because it goes around the sun, and we also go around the sun, and it's kind of moving slower than us, then if you look at it, it appears to go and slow down, and sometimes go back in itself, then forwards again. And this is a problem, because back in those days, the assumption was that the sky was perfect, that the sun was, that the Earth was the centre of the universe, everything went around the Earth, and that stars described perfect circles around the Earth, and that the planets also described perfect circles around the Earth. And Kepler could not make this work. So he had to do two things here. Firstly, he had to abandon the idea that the Earth is the centre of the universe. In fact, this wasn't new at the time. A Polish priest called Copernicus figured that out earlier, 1543. And also, there were quite a few people in ancient Greece who had suggested the same thing. There's some obvious reasons for it. And so he got rid of the idea that the Earth is the centre of the universe, fine. The next thing he had to do was get rid of the idea that planets move on these nice circles, because they don't. What he did was introduce the concept of them moving on ellipses. So instead of nice like that, you go like that. And when they move on an ellipse, they've got to go faster at one bit and slower at the other bit. They go faster when they're going past the sun and slower when they're further out. And with these two things together, he was able to explain the orbit of the planet Mars, and he developed a set of laws as to how things move. And that is now still what I teach my undergraduates. Keplerian motion. I use Kepler's laws and Kepler's equation because it works. That is what celestial mechanics is now. However, he didn't really know why. So let's move on to the next person. Good old Isaac Newton, one of the greatest scientists the UK has ever produced. Now, Newton himself was slightly mad. He spent the majority of his time discussing and writing on religion and on alchemy. And less than half his time writing on science, but even in that time, he completely revolutionised physical science. He put a natural mechanical basis for understanding what goes on in real life. One of the things he did in particular I want to pick out, and it was produced in his Principia, his Philosophiae Naturalis Principia Mathematica, or it's usually shortened to Principia. The translation, of course, is the mathematical principles of natural philosophy. It's the idea of trying to explain what goes on in the world through force and motion and things like that. And again, this is what we teach our first years. I've just been doing that. From within Principia, there's one important thing I want, which is Newton's law of universal gravitation. And that states for the first time that the gravity which acts on Earth, which causes this to fall, that is the same gravity as causes planets to go around the Sun. And it depends only on the masses of the two objects and how far apart they are. And because it happens everywhere, he called it universal. And that is the reason why planets follow the orbits that Kepler set. It's because of Newton's idea of gravity. Now that's only an approximation. Relativity kind of killed that, but gravity still works very well on large scales and when you're not moving too quickly, and it's still what I use in my research. Next, rather less well-known figure, a guy called the Reverend John Mitchell. He was a Cambridge Don for 20 years. He gave it up to get married and spent the last 40 years of his life as a vicar at Thornhill in Leeds. He was also a scientist, and he was the first person to look into the night sky and think, those stars aren't in the right place. The reasoning he had was that if the stars had just been all placed randomly, they would not have ended up bunched in the way they are. And he thought that both about binary stars, about which you can see quite a few with the naked eye, but in particular about clusters of stars. Now I want to illustrate this with the Pleiades cluster here. Now the Pleiades is again a very well-known winter object. It's one of the most recognisable things in the night sky. It's visible right now. If you go out, look south, find Orion, go up, there'll be a bright star called Aldebaran. Jupiter's there right now. Up a bit further, the Pleiades is a set of 7 bright stars. The idea was, from John Mitchell, that these stars are so bunched together, it's completely improbable that happened by accident. And therefore, there must be some physical connection between these things. And he was absolutely right. They formed at the same place, same time, and they've been together ever since, but they'll gradually drift off and dissipate over time. Our own sun was probably born in the cluster of stars a long time ago, but we can no longer find which cluster. Next, you will have heard of this person, William Herschel, who again one of the greatest British astronomers. He was German. He came over here aged 21. As a musician, was a professional organist in the city of Bath, and wrote a large amount of classical music. Last time I checked, it was 24 symphonies, assorted other pieces. He's still known to Classic FM, but from our point of view, he's interesting because A, he was a brilliant telescope maker, by far the best there's ever been. B, he was an excellent observer who could systematically look through the night sky strip by strip and find stuff that nobody else had found. C, discoverer of the planet. Who remembers this one?
Uranus?
Yes, discovery of Uranus. It was not an accident. It's because of systematic study that he discovered it. It would have happened a month later, a month before, depending where it was in the sky. So one thing he did, which what interests me, was start looking at binary stars in the sky. He found quite a few stars which are close to each other, And the idea he had was that there are probably two stars at very different distances. So if I assume that one's fixed, I can look at this one and try and work out how far away it is from how much it appears to wobble because the Earth is going around the Sun. That failed completely because these binary stars actually were orbiting each other, and so the motion was nowhere near what he was expecting. But instead, he discovered the first orbital motion. He spent 40 years looking at this particular object, Castor, another bright star in the Northern Hemisphere, and he found that you could see two stars, and over those 40 years, one had moved slightly compared to the other. And he was able to actually measure from that the period of the orbit at 342 years. It's quite an achievement at the time. The most recent result I have for this was by one of my colleagues, Willie Torres. Only a couple of years ago he had the definitive paper on this, and the orbit period is now known to be 459.1 years, which means that William Herschel was pretty close. So I'll give him that one, and by the way, he originated the term binary star, so I like him anyway. So that brings me nicely to the first type of binary star, which is what I call the astrometric binary. And this is one where we see two stars in the sky, we can measure how far apart they are, and we can measure this angle of where they are versus true north. And as they orbit, that angle will change, their separation will change, and if we just watch over a long period of time, we can track the motion of one star versus the other, we can work out the orbital period of the system. We can also work out the masses of the stars, but we can't quite do it. Rather irritatingly, we can work out the sum of the masses. That's just Kepler's third law. That's what it gives us. We can also find the orbital inclination, and by that I mean if you've got an orbit with a binary star system like that, it's important whether or not it's like that or like that compared to the observer. If it's like this, it's edge on, and it's got an inclination of 90 degrees. If it's like that, it's face on, has an inclination of 0 degrees. We can have everything in between because we do not occur in a special place in the world, in the universe. So these things will be randomly distributed compared to us. So we get the inclination, we need that. The other thing we can get from this is the eccentricity, in other words, a measure of how non-circular the orbit is. So if I draw a circular orbit here, that's got an eccentricity of 0. If I draw quite a flattened one, I have an eccentricity of 0.5. If I flatten my orbit so much it's just a straight line, well, that's an eccentricity of 1. This makes a big difference. This is in all the equations, so I do have to worry about it, even if I'm not interested in it. And these objects give us that. Okay, let's move on next to a different type of binary star. And this is one where we look at the spectrum of the star. And here I have, fingers crossed, a demonstration. This is not a very good demonstration, but it's the best I can think of since yesterday afternoon and the stuff we had lying around in the laboratory. So if I take this, there we go, put it on there, on the plug, and this as well, and then turn this object on. Why is that not on? There we are. That's better. I might take another one off, just temporarily. So, this is slightly underpowered, apologies about that. This is a standard light source like we use in the laboratory to do optics experiments, and I've just passed it through a slit here, and you see the light coming here. Now what we can do is we can take a prism and put that in. If I get this right, there you see the light has been split according to its colour. Now I'll try and turn that up a bit. There we are. That's as far as I dare take it, because when I practiced this afternoon I blew one of those. I have got a spare, but I don't want to kill two in one go. The lab tech might start looking at me with concern. I'll turn it back down a bit now before it does blow. This is a smoke. So, I take my white light, I pass it through a prism, and you can see it's split into the different colours. Now, one of the things that us astronomers like to do at a telescope is exactly that, but with light from stars. But in our case, we've got more money, so we don't have a prism costing £1.50. We have diffraction gratings costing thousands of pounds. That's another story. And we split this light out a lot, so we can really start to discern the differences in light from the blue to the red of a star. And so, irrespective of a star, it will be big in the blue, go down in the red like that. Let's say blue, green and red. And if you have a hot star, it'll be brighter in the blue. If you have a cool star, it'll be relatively brighter in the red. But on top of that, there's all these little absorption lines that go down like this, in random places, and each one of those absorption lines is caused by a single chemical element in the atmosphere of the star. That's what a single star looks like. Now, if I now have a binary star, I'll find that those absorption lines are suddenly split into two, like this. And that only happens if you have a binary star system and the two stars are moving at different speeds relative to us. So if we have a binary star system, one star is coming towards us, the other star is going away, the Doppler effect says that the light from the star coming towards us goes to the blue, and the light from the star coming away from us goes to the red. So the spectral lines will split like that. We can see that, and we know we've got a binary star. And the guy called Edward Pickering was director of the Harvard College Observatory in the late 1800s, early 1900s, and realised that he started to find these things. He was experimenting with photographic spectroscopy of stars, doing things like this, basically. And he noticed that if you look carefully at the star Mizar, he sometimes saw two spectral lines instead of one. Other times he didn't. And immediately after that, one of his assistants, Antonio Mori, noticed the same thing for another star called Menkalinen. And here I managed to find off of Wikipedia an image of Edward Pickering, it's that guy there, and his computers, the Harvard computers. Now, at some point, Pickering decided that the males he was employing were rubbish. Women would be better. So he hired a pile of female scientists, mathematician, astronomer types to do the computing and some of the observing for him. They became known as the Harvard computers, and one of those discovered this doubling of these spectral lines for only the second time. Now I wanted to mention this really because it's important to remember it shouldn't just be all men doing this kind of thing. And so I want to illustrate what this looks like a bit more closely. So in my next plot here, I've plotted a spectrum I took at the Isaac Newton telescope in summer a couple of years ago. And you'll see here, these are the absorption line things I was talking about. This is in the blue region of the spectrum. All that spectrum you see there is just a small part of the blue, so I've been dispersing it out a lot. And you'll see that each of these lines is doubled, there, there and there. This is a hydrogen line. This is a helium line. That's another helium line. And the only way we could explain this kind of thing is if we've got a short period binary star system, one star is coming towards us quite quickly, the other star is going away from us quite quickly. And then the Doppler effect shifts their lines. I can measure the positions of those lines and use the Doppler effect, Kepler's laws and Newton's gravity to get the masses of the stars. That's why I'm interested in this. Now, if you just talk about spectroscopic binary stars, that's quite nice, but there's limitations. We can get the orbital period, that's fine. We can get an idea of the masses of the stars, but we only get a lower limit. Because if I have stars of some mass in an orbit like this, if I tilt it and double the mass of the stars, it will look exactly the same in the spectrum. So I can't tell those two cases apart, and therefore I only get some lower limit on the masses of the stars. And finally, I get this eccentricity parameter here as well, which is important. So that's nice, but that's still not the whole story. So now I want to move on to the type of binary star which I personally am most interested in, which is eclipsing binary stars. And this is started off by a guy called John Goodrick. Now, he was born in mid-1700s. He was deaf from childhood. He started the field of eclipsing binaries with this paper in 1784. A year later, he started the field of Cepheid variables, another way of determining the size of the universe. And shortly after, he died at age 21. So, impressive. And in fact, if you go to York now, there's a blue plaque for him. He used to observe from a house behind York Minster. And he would measure the brightness of stars. He noticed that Algol was getting fainter every 2.9 days. And he was the first person to suggest, maybe that's because there's another star which is much fainter and it's going in front of Algol and blocking out some of the light. He's absolutely correct. And if you want to, you can go there now, and you can go around this house. This is a treasurer's house. This is a picture that I've taken from the top of York Minster That is the nave over there. This is a chapter house. Here is the treasurer's house, and that is a window he observed from. Somebody's written an entire scientific paper trying to work out which window it was. 1948, the Observatory magazine. The room doesn't exist anymore. They took the floor out to enlarge the Great Hall. But if you want, you can rock up and go around the house. It's owned by the National Trust. And you can see where he observed from. So what he would do is he'd sit there at night and he'd watch stars disappear behind the cathedral. And he'd time when they disappeared and using that to figure out the positions of the stars in the sky. And so he came up with the idea of eclipsing binaries. Now this is what a modern look of eclipsing binaries is. So what I've done here is plot up the variation brightness of one of these things for a period of around about, 13 days. These data come from a small space telescope operated by NASA. And you'll notice that every 2.5 days or so, we've got this big dip in brightness here. That's a primary eclipse. There's another one there. And that's when the cool star goes in front of the hot star. And half an orbit later, the cool star goes behind the hot star, and we have a shallower dip that looks like that, or that. And I can say immediately here, the orbital period is time from then to then, or from then to then, or from then to then. It's really, really easy to do. I can also say that these eclipse lengths here depend on how big the stars are. So if I have wider eclipses, that means bigger stars. And therefore, I can use these eclipses to measure the size of my star. And that is what most interests me, because it's almost impossible to do normally. So from a light curve like this, we can measure the orbital period of the system. We also get the orbital inclination, which is missing before, and we get the radii of the stars. So we put this together now. Backwards. And I want to give you just an example of my favourite type of object, which where you have stars which are in a binary system, they're eclipsing and they're spectroscopic. So you see these double lines here. From the spectroscopic orbit, like you see here, we can measure the masses. Now, I've just done this plot quickly. I pulled some data from a paper in 2020, which is the most recent study of this object. This star is called Menkainen, Beta Aurigui. Again, it's one of the brightest stars in the sky, and it's also, I think, the second brightest known eclipsing binary. The first one ever measured this way. And from this, we measure masses, which look like this. Now, I'm not too worried about remembering the numbers here. The only point I want to make is that the L bars here are really small compared to the numbers. We're measuring masses to 0.3%. So we have a radial velocity curve. Next, we need a light curve. This is the one which was done back in 2002 by a very small telescope from NASA, which broke before it got properly into orbit, and they used it to do a little bit of bright star photometry whilst they're at it. And with that, I was able to measure the radii of the stars here to 0.5% precision. There's a lot more goes into this. This, from the top half of the slide to the bottom half of the slide, is about a 10-page paper. So I've swept all the details into the carpet, because I don't really care about those right now. What you want to know is, what does this look like? And the answer is, we can look at one of these things, we can measure mass to 0.5%, we can measure radius to 0.5%, then we can go to our favourite theorist and say, your models of stars, do they match what I found in real life? And they can either go, yeah, everything matches, in which case we say, good. Or they can say, oh, my models don't work. I'll get back to you, and hopefully they'll improve their models, we'll understand stars better, they'll come back, and that's how science works. So, to summarise what we know, I've done the next slide. Roughly 350 eclipsing binary stars like this are now known. And I maintain a catalogue of this online, so I can easily look up what's going on at any time. And this is what it looks like. This is the only big plot in the paper, in the talk, really. So on the x-axis, I've put the mass of the stars. Can I do this? No, that's still not working. On the y-axis, I've put the radius of my stars. Notice that both of these axes are logarithmic, because otherwise everything will be squashed into the bottom left. And here we can see a great pile of stuff in the middle. The sun would be here at 1 and 1, because this is all measured in solar units. Lots of stars here between 1 and 2 solar masses. That's because they are quite common, they tend to be quite bright, and they are easy to study. If you look at massive stars up here, they are much less common, but they're very bright, and they're really difficult to study because you get things like winds, mass transfer, interaction, very, very fast rotation, so they're hard, there's not many of them. If you go down here, these are low mass stars. They trace all the way down there. All these stars are sat there for millions, well, billions of years, just burning hydrogen in the core, doing very little else. And there's not many of those either because they're intrinsically faint and because they're difficult to study because of magnetic activity. If we go up here, we've got all the giant stars. They're difficult because if you have a giant star in an orbit, you've got the star's got to be further apart, and that means the orbital period has got to be hundreds of days. Which means to do this kind of thing, you ideally want your own telescope in 10 years. People have that, and they've done it. It's great, I just report the results. Finally, over here, you see these little things dotting up. Now, these stars cannot have been here for millions of years and then got bigger as they evolved over time because the age of the universe is not enough. So these stars have got to be still forming, so they'll have formed up here somewhere, they'll have moved down as they contract, and they're still going before they get down to here. We've caught them in what we call the pre-main sequence phase. Rare, but very interesting. Right, so next I want to move on to the actual stuff I do, which is the weird and wonderful. So I had the idea, it kind of came to a head over COVID, to be honest. I spent a lot of the time in the study looking at what the space telescopes had done for me and realising I don't need to go observing to get light curves like this myself anymore. In the olden days, I'd go to a telescope for 14 nights and get data much worse than this. Now I can go to the NASA website and download something much better. It takes me 30 seconds. So what I have here is an eclipsing binary. Primary eclipse, secondary eclipse, primary eclipse, secondary eclipse. That's fine. And on top of that, I have a pile of what the technical term is wibbling around. And that's pulsations. And that's important because if you think about the physics of the Earth, a lot of what we know about the core of the Earth is from seismology, the study of how oscillations from earthquakes travel through the Earth. We could do exactly the same thing with stars. We just call it astroseismology because it sounds fancier, and fancier means grant income. So we call it astroseismology, and what I intend to do is measure the masses and radii of these stars, and then a pile of these pulsations, and go to our tame theorists and say, can your models match this now? Because these pulsations are travelling through most of the interior of the star, and therefore they hold information on what's going on inside the star, something we can't see directly ourselves. This is our only way of peering inside a star, and what I want to do is do it for stars of known mass and radius. So here's another one. This is HD 23642. It's quite a bright star, a different kind of pulsation here. This is what we call delta scuti pulsations. They occur near the surface of the star, and they happen in a much shorter time scale. So typical time scale, maybe half an hour to 2 hours, maybe to 3 or 4 hours. You can cover a couple in the night sometimes. And it's much less obvious, but you see here, primary eclipse, secondary eclipse, and that out there looks like it's a bit noisy. That's not noise, it's pulsations. And the great thing about this star is it's in the Pleiades. It's, in particular, that star there. And so, what we can do is we can go and measure the masses and radii, we can measure the pulsations, and we can then use the fact it's a member of a cluster of stars to get some idea of age, and go to our theoretical models and say, do your models fit this? And our theorists will either go, yes, I think I know what's going on, or they'll go, no, I need to improve my understanding of stars. In this particular case, we can measure how fast one star is rotating, simply from the way it changed the pulsations. And that was useful in itself. But I want to go to more massive. This is now around about 14 times the mass of our Sun. You see here nice deep eclipses. These go flat at the bottom. They're total eclipses. They are my favourite kind because they have the most information. If you look further up, there is all that wibbling around again. That is pulsations. And in this particular case, the two stars are quite massive, quite large, in a relatively short period orbit. They are so close together, they are tidally deforming each other. Their own gravity is deforming them into kind of an egg shape. And that changes the pulsations. So the pulsations I see have been affected by the fact in the binary star system. A theory for how that happens has just been produced. I intend to test it. And another one. This goes in a slightly mad pile, I think. D1765 Cygni. This is a massive star. It's about 20 times the mass of our Sun. And it's a supergiant. And it's in the 14-day orbit with another star which is about 15 times the mass of our Sun. It's a giant, and the eclipse there there, and there. And the supergiant outside Eclipse is doing all this weird stuff. Now those are stochastic pulsations. They are caused, we think, by gravity waves. Don't ask. These pulsations appear suddenly. They die off over the next couple of days and go away, never come back again. But there's lots of other ones always happening all the time. So this light curve looks different every time you look at it. But interesting all the time. Now we think this will tell us what gravity waves are doing. And we also think that gravity waves change how stars evolve. We think it will make stars be able to get older before they go bang. But no one's yet really figured that one out. And one of the last things I did this summer was talk to a colleague in Belgium and say, could you observe this star for me once every couple of nights for the entire year, please? And when those data come in, I'll be able to measure mass and radius, I'll be able to measure these pulsations, I'll get the full property of the star, I'll go to my theorist and say, do we think we know what's going on here? And so I want to conclude with the final slide of what's going to happen in the future. And for me, that is another space mission. We live actually through a time of revolution in astronomy with these small space missions which have been sent into space since about 2007, 2009 and so, trying to find planets. And to do that, they've got to measure the brightness of the stars very, very precisely for years continually. And that is perfect for doing eclipsing binary stars. And so, when I used to go observing, I don't have to do that kind of thing anymore, at least not to get brightness measurements. I stand over to NASA, I could do far more than I ever used to be able to do so, and this is the next one which I'll be able to work with. It's called PLATO. It stands for Planetary Transits and Oscillations. The European Space Agency intend to launch it in December 2026. I really hope it's not going to be the world's most expensive firework, but you can never really guarantee these things. But it will move out to a point beyond Earth, in the opposite direction from the Sun. It will sit there, and for at least 2 years, it will just monitor 500,000 stars. At least 10,000 of which will be eclipsing binaries. And I'm in charge of that. So that's my research for the next 10 years sorted. Okay, thank you very much. I'm very happy to take questions.